Okay, so we're going to build a motor, and we start with a nail that's got its head cut off, and we'll wrap wire around it. And then we'll send current through those wires, and that will cause one end of the nail to become a magnetic north and the other a magnetic south. And I would in fact like you to figure out, is the current flowing up through this wire? Of course, these wires are looped around the nail, so on the back side it would be going the other way. But is it going up through this wire or down through these wires across the front in order to make that be a north up there? Now you put that on your worksheet. And then this nail I'll put on top of the glass tube so that it has a pivot that it can turn around. And then I will introduce permanent magnets. These are called field magnets. They create a magnetic field, and this magnetic north sitting in this magnetic field will be repulsed by this north and attracted by that south, and the result, no, this is too good. The result is going to be that this thing will turn, that the north will repel the north, the south will repel the north, it will turn around that pivot, and we are full of joy because we have built a motor just like Mr. Houghton said, until it gets to here, at which point there is no longer any reason for it to turn, that the north is attracted to the south is attracted to the north. So we only get a half a turn out of this motor, and it's supposed to turn for 3 minutes. How can I get it to keep turning? Well, if I could change that magnetic north into a south, and this south into a north, then it would keep going. That where you see N, think that that's an S, and where you see S, think that's a north, and bingo, it would keep going. But how? How can I change the direction of the current flow? And the answer is that we add a conductive loop of wire that is attached to the armature. So when the armature turns, the conductive loop turns. We call it a commutator because it commutes. It drives to work and then it drives home every day. Another name for this is a split ring. Perhaps you would call it a split ring commutator. And then I introduce pieces of metal which will make electrical contact, but they will only touch lightly on the commutator. We say that they brush. And if this one is a high potential, then the current will go from this high potential onto this conductive pathway here, and then there's a wire that goes out and down this loop, all of these loops around the nail, and then there's a wire that comes to here, comes over to this contact point, and the circuit is complete. So that's how I get current to flow in here. But further, as this turns, we need to go to the next page. As this turns, the commutator turns with it, and that gap move, the brushes stay still, but note that right at the moment when the armature is lining up with the magnetic field, that is the moment when the brush is crossing the gap. We're going from this half being the high potential half to the other half being the high potential. Crosses the gap. Which end is the high potential? Changes, and when it changes, now the current is going to be going down the loop this way, whereas before it was coming in here and going down the loop that way. I have changed the direction of the current flow, and thus we make a successful motor. And every half turn, every time it lines up with the magnetic field, that's when the brushes are crossing the gap. Line up, cross gap. line up, cross gap. Excellent. We have an excellent motor, and it will run for 3 minutes, and we are so proud. Now, let me take a break from motors for a minute to point out that if this exact same arrangement was used, but instead of sending a current through the wires to get motion out, I instead put motion in. That is, I took this armature and I made it spin. If the armature spins, then here you would have maximum flux through those coils, and when they get up like this, well, we'll put them like that, you would have no flux through the coils. I should have had them like this. Maximum. None. There would be changing flux through the coils. And if you have changing flux through the coils, we know that that is going to induce EMF. It would cause one end of this to be high potential and the other end to be low. It would cause current to flow, and that would then cause this, which is associated with the low potential end, to become a low potential brush, and this to become a high potential brush. That what we would have instead of a motor would be a generator. It would generate current, and while for half a turn from here, here it's zero flux, and then the flux starts, here it is maximum flux, the most magnetic field through those loops of wire, and then as it turns, the flux gets less and less. We have decreasing flux, and so the EMF is going to flow to oppose that, but then it starts to go through in the opposite direction, which is a continuation of that flux. The EMF continues to be in the same direction, but then when we get to here, the flux is going to start changing in the opposite direction. And so for half of a turn, this would be the high potential end, and then for the other half of the turn, this same end would become the low potential end. And if we didn't have these split rings, then these brushes would flip their polarity. But because of the brushes, it's always the same half the commutator. The high potential side is always touching this brush, and so it is a DC generator. That device, which works as a DC motor, would work just as well as a DC generator. Now I'm going to fiddle things, and instead of a split ring commutator, I'm going to have two solid rings. This solid ring always touches this brush, and then there's a wire from it that goes to one end of the armature. This solid ring here always touches this brush, and there's an end, a wire that goes to the other end of the armature. Well, heavens, if that's the case, how are we going to change the direction of the current? We're going to have a motor that's not going to work. Every time the armature lines up with the magnetic field, it's going to all be over. Unless the brushes themselves changed their polarity every time the armature lined up with the magnetic field. For the armatures to be changing their polarity is to have AC, and this would be a motor that would work on AC, as opposed to the previous one with the split rings, which worked on DC. That it would only work if these brushes changed their polarity at precisely the right moment. the moment when the armature was lined up with the magnetic field. We speak of it as an AC synchronous motor. The motor is going to turn at exactly the same rate that the current here in these wires changes its direction. And we use these kinds of motors in clocks because if you send in 60 cycle electricity, AC electricity into the clock, then the motor will turn at 60 hertz. And then we can use that to time things. We use it in a lot of other things. You get into trouble when you take those things over to Europe where they run their electricity on 50 hertz. But that would be an AC synchronous motor. But note, if instead of putting AC electricity into this thing to get out motion, I put motion into this thing, then again you would have changing flux. That would induce EMF, and that would cause these wires to have electrical potential. And when this thing had gone through half a turn and the change started to be in the opposite direction, so the induced EMF was in the opposite direction, that would produce opposite directions EMF in these brushes. So the same device that works as an AC synchronous motor would also work as an AC generator. And I will show you this in class, and I hope it makes more sense then. And if it doesn't, you must demand of me that it makes sense. I don't know what that picture's about. So here you have a practice. This is a split ring, so that would be a DC motor, or possibly a DC generator, but we're using it as a motor. And the question is, should the brushes be at 1 and 1, or at 2 and 2, or at 3 and 3, or at 4 and 4, in order to make this be a successful motor? Remember that the commutator is attached to the armature, and as the armature turns, the commutator will turn as well, and its gaps will turn. The brushes do not move, and I want the brushes to be crossing the gap when the armature is lined up with the magnetic field. Carry on, my faithful ones. This looks sort of like the picture we had before, except I no longer have permanent magnets as my field magnets. Now I have electromagnets out here as my field magnets. Well, that is exactly the motor that you are building for me. And it is still the case that when this armature lines up with the magnetic field, that's the moment that I want my brushes to be crossing the gap. Oh, we've got it just right. But what if instead of feeding DC current into all of these coils, I fed AC current in? Oh no, the current would change direction in here when the AC changed its direction. That would cause this north to become a south. So I'd have a motor which had north repelling north, and then when the north changed into a south, it would be attracted back. And then it would change back into a north, and it would be repelled, and then it would change back into a south, and it would be attracted back. This thing would just jiggle, 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 jiggle. Oh, horrors. But no, Mr. Houghton. If you fed AC current into these wires, you would also be feeding AC current into these wires. And when the current changed its direction, causing this north to become a south, it would also change direction here, causing this north to become a south, and so these would both have the same polarity. They would repel, even though they're now both souths. And then when the current changed direction again, they would become both norths, and so it would repel through a whole half a turn, with this end always being the same as this field magnet here, until it comes to this point, at which point we no longer want this one to be the same as that one. We want this one to become opposite to that one. And that is accomplished by the brushes crossing the gap. So this motor here with this split ring, but with electromagnets instead of permanent magnets, would work on either AC or DC current. It is called a universal motor. And the rate of turning of this motor would depend on how strong the current was, how strong these magnets became. So this is a motor which will speed up and slow down depending on how big you make the voltage, how big you make the current that flows through it. Not true for an AC synchronous. And so this universal motor, if you have a motor in your life that you can change the speed of, it's probably a universal motor and would work off of a battery if you could get the voltage high enough, as well as it works off of the current you get out of the wall. This arrangement, however, would not work, at least not easily, as a generator, because if you were not to send current through, then these field magnets would not become magnetized, and if you were to then start turning this thing here, there would be no magnetic field that it was turning in, and there would be no change in flux, and so this would not work as a generator. So in your notes you have this picture, and it's left without any commutator, but it has these rectangles indicating permanent magnets. If you had a split ring commutator, this would be a DC motor, and if you had solid rings, this would be an AC synchronous motor, and this same device would also work as a DC generator or an AC generator. Here is the one with electromagnets out there as field magnets, and that would be a universal motor. It's got a split ring. And here is the third motor that you are supposed to know about. Here it is down here at the bottom. But the story begins up here with the generation of the electricity. If Dominion power causes not one coil but 3 different coils to spin within a magnetic field, then they'll be changing flux through each of these coils, but they will not be in phase with one another. From the black coil we would get this current flowing, and from the gray coil from the intermediate colored coil we would get this one here, and from the gray coil we would get this one here. They are out of phase. We call this 3-phase electricity, and that's what Dominion power ships across the countryside. If you look at the big power lines, you will see they come in triples, and they are carrying 3-phase electricity, one in each of the sets of wires. And then if I am a captain of industry, here is my motor there in my factory, and I get this 3-phase electricity delivered to my factory, and I take one phase and I hook it up to these field magnets, and I take the next phase and I hook it up to these, and the next phase and I hook it up to these. And here is my armature, but it has no wires wrapped around it. And so the current peaks first for this coil here, causing this to be a magnetic north, and over here is a magnetic south. And then that current begins to fall away, and as it does, the next current rises to a peak, causing this to become a strong magnetic north. And then it fades, and the next one rises to a peak, causing this to become a magnetic north. And then it fades, and as it does, this black one rises to a peak in the opposite direction, causing this to become a magnetic north. And you can see that these norths are running around in a circle. And so my armature only needs to be a lump of iron, like a paper clip. And these this magnetic north, as it runs around in a circle, drags the paper clip behind it. This is called an induction motor because the armature does not get magnetized because we send current through a coil. It gets magnetized by induction. This, for reasons I don't understand, tends to be a much, much stronger motor. And so where you have large appliances, this is the motor that you use in the factories. But the compressor in your refrigerator is an induction motor, because it needs to be very strong. The compressor in your heat pump, if you have a heat pump, I'm assuming you have a refrigerator, is going to be an induction motor. But wait a minute, Mr. Houghton, we don't have three-phase electricity coming into our house. You're right. There's another tricky way to do it, and if you're curious, you can ask me and I'll tell you. Another advantage of this motor is that without a commutator and brushes, you don't get sparks. So this is an ideal motor to use in a gas pump. I don't like sparks around gas. Or in a grain elevator where you have dust that could explode. This would be the motor you would want to use because you don't want sparks. And your gas station is not getting three-phase electricity either. So just like your refrigerator, we have to figure out another way to take single-phase electricity and turn it into three-phase, and there is a clever way to do that. Here are images. This is you see the split rings and the permanent red and blue field magnets. This would be a DC motor, or it would be a DC generator. If you made that spin instead of sending electricity in to get spin, if you put spin in, then you would get electricity out. Here is a more sophisticated motor. And you can see instead of a pair of split rings, this has many, many splits. There's about 8 pairs here. And then there's associated windings on the armature going with each one of these. And so there's brushes. Here's one of the brushes. And as it touches, it powers up one of these. And out here around the outside, we have electromagnets. So this motor ought to either work on AC or DC because it has electromagnets. This ought to be a universal motor. This is an induction motor. There are no brushes. There are no coils wound around the armature. That it looks kind of specialized, but it's just a lump of iron. And then out here are field magnets around the outside, many of them, that cause a magnetic field that goes running around in a circle, and this lump of iron chases after them. Here in this box here is the place where we put those special tricks that I talked about, which can turn single-phase electricity into three-phase electricity to make this motor work. Thank you very much.